Good morning, everyone. My name is Yanhong Xiao. First, I would like to thank the organizer for inviting me. It's a great honor for me to be speaking here. Other than the topic that I have promised to talk about, which is spectroscopy and the spin squeezing using weak measurement, I will also add a part which is on quantum control at a distance, since this is a workshop on quantum control. So as I said, my talk will introduce a spectroscopy method, which is based on weak measurement, which allows us to have resonance line width below the limit set by the coherence lifetime. And then I will show you how we apply it to a magnetometer to achieve good sensitivity. And then I will talk about how to achieve atomic spin squeezing, especially when the atom-light coupling strength is very low. I will tell you two theoretical proposals that we came up recently. And then I will tell you two examples where we do quantum control at a distance, which I will tell you what we mean by this. So first, we know that in spectroscopy, we want to have a narrow resonance. We know that nowadays frequency is the parameter that we can measure most accurately. We know that if the resonance is narrow, we can locate the center of the resonance very precisely. However, we also know that the narrowest line width we can achieve usually cannot be smaller than the line width set by the 1 over lifetime, which is the frequency-time uncertainty relation. So here the lifetime means either the coherence lifetime of the target resonance that we use, or equivalently the interaction time that you can have. However, people can still achieve line width which is much narrower than this limit. For example, in the 1980s, many people used the spectroscopy, the Ramsey spectroscopy method to achieve Ramsey fringes, which has a line width much smaller set by the coherence lifetime, simply by using a very long dark evolution time. So in this paper, Metcalfe and Phillips analyzed how good this method is for precision measurement. And they say that they found that although the line width of the Ramsey fringe decrease with the increase in dark evolution time, the contrast of the fringe or the amplitude of the resonance decrease faster. So as a consequence, the resolving power of the resonance, which is defined by the line width of the resonance divided by the signal to noise, is decreased. So therefore, when you look for a line narrowing mechanism, you have to also pay attention to the signal to noise. So here I will tell you a different method that allows us to achieve line width smaller than the coherence lifetime limit. And the system we use is the so-called EIT resonance. So in case some of you don't know EIT, usually in EIT there are two optical fields that drive two different transitions. And when the two-photon resonance condition is met, both of the optical fields, although both on resonance, are transmitted instead of being absorbed, giving you a transparency window. And this window can be very narrow as the decoherence rate set by the two ground state. And such EIT spectra has been used, for example, in atomic magnetometers to make the most accurate, most sensitive magnetometer, or used in atomic clocks, for example, those CPT, coherent population trapping clocks. As I said, however, the linewidth, the narrowest linewidth you can achieve is set by the coherence lifetime. So we propose a different method to do this. So instead of measuring the transmitted power in the EIT, we propose to measure the so-called second-order intensity correlation between the two EIT fields defined by this formula. So how do we have intensity correlation? Well, we marginate the two EIT fields in a common way so that this frequency modulation will be converted into intensity modulation once they interact with the medium. So here I show that if your two-photon detuning is 0, then the frequency modulation conversion to intensity modulation between the two EIT fields are completely in phase, so that you get a G20 of positive 1. However, once you have a tiny offset deviation from the two-photon detuning 0, the transmission spectra of the two EIT fields are offset by an amount which is much bigger than the actual two-photon detuning due to the ground state coherence effect. This is also understood as a nonlinear Faraday rotation effect if you were to measure the rotation in this field, in this system. So as a consequence of this offset, the conversion from frequency modulation to intensity modulation between the two fields are out of phase from each other. That means that we will get a G20 value of -1 immediately. So theoretically, we proved that this is true. Indeed, the linewidth that you can get is smaller than the decoherence rate set by the two ground states, which is gamma 2 here, divided by a parameter which is usually much bigger than 1, determined by modulation parameters. So this is the proof of principle experiment that we did a few years ago in a vapor cell that has no anti-relaxation coating on the wall or no buffer gas. So the intrinsic linewidth is of the EIT is set by the transit time. Sorry, can I have another pointer? Can I borrow your pointer? Thank you. So experimentally, we proved that indeed we can have a G2 resonance which has a linewidth much smaller than gamma 2. So on the left is the experimental correlation signal that we get from the two EIT fields. You can see that the correlation between the two. Okay, thank you. Are completely overlapped, so you get G2 value of 1. And once you have a smaller two-photon resonance, two-photon detuning, you get a G2 value of -1. So this width is very narrow. And we checked that we have some enhancement in the resolving power, so we are not sacrificing the signal noise too much. However, we are interested to in applying this spectroscopy method to atomic magnetometer. So for that, we want to use a vapor cell that has a special coating which allows you to have a very long coherence lifetime, therefore very good magnetometer sensitivity. So in such kind of cell, we have a G2 linewidth down to almost 0.13 hertz. It's about 20 times smaller than the intrinsic width set by the coating quantity and the magnetic field gradient. However, when it comes to the sensitivity of the magnetic field, we are limited by residual amplitude modulation in the laser. As I just mentioned, we have to apply frequency modulation in this method. So for that, we came up with a weak measurement approach. So just in case you don't know about weak measurement already, I use this canonical example for weak measurement to show you what this means. So this is the Stern-Gerlach experiment. You send a spin through a magnetic field gradient, and spin half and spin down particles will be separate in space. However, what if the magnet has a very weak gradient? Then, and also plus the incoming atom flow will have a spread in its wave function to start with. Then it's very hard to distinguish between spin up and spin down, so because the two wave packet will be overlapping. So in weak measurement approach, you apply a post-selection step, where you have a strong magnet placed in an orthogonal orientation to the initial one, so that you choose to measure the spin right. And that spin right, as we know, is a coherent superposition, or it's a superposition of spin up and spin down, but with a negative sign. So as a consequence, you are not measuring this merged wave function. Instead, we are measuring this little bump, which is a difference between these two, and then you do the probability. And this little bump has a very large offset from the middle, which gives you a much cleaner signal to measure. So this is the essence of a weak measurement, where you simply choose the right input state and the output state, so that the input state and output state are almost orthogonal, but not exactly orthogonal. And that gives you a so-called weak value to amplify your signal. So in this reference, you can find all this formula for this weak measurement if you are interested. Weak measurement has been used in many applications, and here there's a very nice review of this. But it looks like weak measurement approach has not been used to measure an atomic resonance. So that's why we want to find a way to use this to improve our measurement. So why is it hard to use weak measurement? That's because it's very hard to identify what is the pointer and what is the system for your Hamiltonian. You have to design a atom-light interaction Hamiltonian so that you can use this post-selection method. So in our EIT system, we can prove that the effective Hamiltonian for light in the system can be written as a product of a pointer Hamiltonian times the system Hamiltonian. And this part means you do a change to your light polarization, and this part represents the change in the frequency of your light, because you are doing this frequency modulation to intensity modulation conversion. So the Hamiltonian kind of correlates the system degree of freedom and the pointer degree of freedom, meaning that different frequency components in the intensity correlation has different polarization change. So by doing a post-selection in the frequency regime like this, meaning that I choose to measure the intensity of the light in such a spectral domain, I can amplify the Stokes vector that I want to measure, which is sigma z. That's directly related to how big the G2 value that I will get. So we can theoretically prove that the line width of the G2 value will be proportional to the post-selection parameter, 1 minus d. And experimentally, we prove that our theory works, and the line width indeed can be engineered by the post-selection variable. And in the end, we can achieve a magnetometer, which has a pretty good sensitivity. And most importantly, it works in a room temperature vapor cell with very low laser power. And in fact, in this regime and in a near DC magnetic field measurement, this is probably the highest sensitivity that one can achieve. And we are preparing this paper. Now, let me move to atomic spin squeezing. We know that once you get rid of all the technical noise, you have to fight with quantum noise. So, this is a Bloch's field that describes the connective spin state of a big ensemble. And this is a coherent state. This is a squeeze state. And the reason we like squeeze state is that the minimum measurable quantity is proportional to 1 over square root of atom number if you are at standard quantum limit. However, if you can somehow do very nice squeezing and even achieve Heisenberg limit, you have a much higher sensitivity, which goes with the atom number. And this is the well-known Wieland criteria to describe how much you are improving in terms of the angular resolving power on the Bloch's field. So there are a lot of work in this field, many methods to do spin squeezing, such as QND measurement-based squeezing, atom-light interaction, and light-mediated interaction. So what we are interested is to look at ways to realize spin squeeze state for atomic system with a very high atom number. So far in cold atoms, the atom number people can have is up to 10 to the 6. And the only experiment in warm atoms has been in Professor Eugene Pauzik's group, where they have 10 to the 8 number of atoms. As I said, large atom number is very important for precision measurement. So we are interested in pushing the 10 to the 8 number even higher. So why? For example, let me give a very simple comparison. So if you have 10 to the 6 atoms and you have 20 dB of spin squeezing, which is the highest spin squeezing one can achieve now in Kasvich group from Stanford. And now imagine you have 10 to the 8 number of atoms, but no spin squeezing, meaning you are just at the standard quantum limit. And in these two cases, you get exactly the same sensitivity. So that means that you are already winning if you have a lot of atom number, even you don't have any spin squeezing. So that's our motivation. But it is very hard to do spin squeezing in large system. So first of all, classical noise tend to dominate over quantum noise because they have different scaling. So if you want to even see the standard quantum limit, your measurement has to be 10 times better in 10 to the 8 atoms than in 10 to the 6 atom. That's the first challenge. The second challenge is that large systems with large number is usually physically large. And it's very difficult to have a uniform control over a large system. And also, it's very hard to apply a cavity. So the atom-atom coupling strength is very low. So we want to come up with spin squeezing schemes that can help you even when the atom-light coupling strength is very small. So in this paper, it's shown that the degree of squeezing, for example, in QND and in two-axis twisting method goes as the coupling strength, which is proportional to photon number and optical depth, photon scattering probability, and so on. So from this comparison, you know that if your coupling strength is small, you want to go to the two-axis twisting scheme, which scales better. So for that, I'm going to skip the details here and just show you from this paper that the two-axis twisting spin squeezing can give you Heisenberg limit compared to one-axis twisting and so on. However, it's very, very hard to design a system that gives you this kind of Hamiltonian. So for example, here are some proposals, including one by Klaus many years ago. So as an experimentalist, we want to look for a simpler setup. So we came across this paper, very nice paper by Takatash. Takahashi group, well, they propose that, okay, you don't need to use cold atom, you don't need to use atom-atom interaction, you just send a coherent beam of light into an atom ensemble. It can be cold, it can be warm, it doesn't matter. So, and then after it interacts with the atom, the light is reflected. But you add a wave plate so that you rotate the quadrature of the light that carries the noise of the atom back to the atom so that you create a nonlinear, effective nonlinear Hamiltonian. So this method is very nice, but the imperfect part is that after the light exits the atom ensemble, it still carries the information of the spin. That means that the process is not unitary. Professor Induich's group, who is also here at the workshop, proposed this method to erase this information carried by light so that the interaction, the spin squeezing can be unitary. However, so this is also an experimental proposal. However, this would require very good feedback and quantum efficiency. So inspired by all this work, we propose to do this eraser or optically. So the scheme has been described in this paper. So we propose that you can pass the light through this atom 3 times, and in the middle you put a wave plate so that the noise that the light pick up from the atom in these 3 paths can destructively interfere with each other. So therefore, when the light exits, it doesn't carry any information, but the atoms are still squeezed. So that's kind of the idea. I'm going to skip all the details and move on to the next proposal, which is to use weak measurement to also improve spin squeezing when your atom light coupling strength is very weak. So, as I said, the QND method scales with the atom light coupling strength like this. And when this kappa here is very small, you get very little squeezing. So how can weak measurement help? So again, we are using this Hamiltonian, JZ-SC. Here, SC is the Stokes vector of the light, and JZ is the spin of the atom, collective spin of the atom. So the JZ-SC Hamiltonian by itself does not squeeze the atom because it's a linear interaction. So in this proposal, we propose that on top of the coherent light that you send through the atom, you send a single photon state mixed with a vacuum on a beam splitter. So why do we do this? That's because that after interacting with the atom, we can combine this single photon state, and at the output, we can do a post-selection. So for example, after the beam splitter, the input light state can be written as this. So 0A and 1 photon at B, or 1 photon at A or 0 photon at B. And the coefficient is determined by the beam splitter. And after interacting, the state has changed. But we can select out this state. So it looks almost the same as the input with a minus sign here. So that state corresponds to no photon click at that detector and only 1 photon click at this detector. You can kind of understand this because at the input, the photon is from here. So if nothing happens, then at the output, the photon should come out from here, right? But now if I say that the output state has to be no photon here, then it means that this state has been changed to a state which is almost orthogonal to the input state. And that's the essence of weak measurement. So this is the math which I'm going to escape because of the time limit here. But I want to show you that by using this post-selection scheme, the squeezing, for example, if you have kappa of 0.2, there's almost no squeezing if you put it into this formula. But by using the post-selection, you can have some squeezing. And also, it's interesting that although you are starting with a QND Hamiltonian, the spin state, the atomic spin state that you end up with is not a QND type of output state. In particular, the zero value for the atomic spin Jz has a zero average value, which is very much like a state that you produce with unconditional spin squeezing scheme. And we also show that when the coupling strength is very small, it's more beneficial for this mechanism to work. That's because there's actually a very simple way to understand how this whole scheme works. So we know that, that if you create a pair of spin, you have spin squeezing. That's kind of a intuitive picture here. So for example, initially all your spin are here, and this strong field is the field that you send in, and this weak field denoted by yellow color here is the weak field that you send in. So if you have the first lambda here, you flip one spin, and then you go through the second lambda here, you flip a second spin. So that means that the photon that you produce you generate in the first lambda is immediately absorbed in the second lambda. So and if these two processes is correlated, you produce a pair of correlated atomic spin. That's how you have spin squeezing. And then you see that in this process, there's no photon that has been produced. That has been produced. That's why the photon set looks exactly the same, except for this minus sign here. So these are the theoretical proposals. We are doing the experiment. And as I said, this is a very, very challenging experiment. And it took us about 5 years to go through all the technical details and learn in the hard way that it is indeed very difficult to deal with large quantum systems. However, we still managed to see some spin squeezing for macroscopic vapor cell. And right now, our squeezing is limited by mostly spontaneous decay, which we are still trying to fight with. Now, let me move to the last part of my talk, which is to tell you something about quantum control at a distance. So what do I mean by this? So as I said, we use vapor cells that has atoms flying around. And if we can coat the wall of the glass cell with some kind of special material that can prevent decoherence when the atom collides with the wall, then you can have very long-lived atomic coherence in such kind of a cell. And in the meantime, the atoms are flying around very fast, 300 meters per second. And in the meantime, if you use atom-light interaction schemes that allows you to have quantum state transfer between atom and light, then you can have a very interesting control between these two light fields, which is spatially separated in a vapor cell. Because the information of this beam will be mapped to the atom, and then the atoms quickly carry the information and fly into everywhere in the cell, and that information can be read out by another spatially separated light beam. much like in a quantum memory. So that's the basic idea behind this thermal atomic motion mediated coupling between distant optical beams. So almost 10 years ago now, when I was a postdoc in Ron Wadsworth's group in collaboration with Misha Lukin, we demonstrated how this kind of flying atoms can be used as a beam splitter for light. So for example, here you send in a control and signal beam to perform EIT, and then this coherence is spread out everywhere, and then in a different channel, even when you only have a control beam, you still have some kind of a signal beam readout. So this looks like the signal input here has been split into two parts. Some come out here, some come out from here. So this is a this is a beam splitter for light using the snow light process. So very interestingly, you can see that only the narrow part of the EIT gets transferred over. That's because this transfer is a relatively slow process that takes the time of millisecond scale. So now there's this natural question, because the previous demonstration is just for a coherent classical beam of light. So can we split non-classical light? And the answer is yes, in principle, because the shared coherence can be used to generate non-classical light anywhere in the vapor cell. So we have a strong motivation to do this, because in a quantum network with many nodes, you want to have a lot of squeezed light beams. For example, people use many sets of OPO systems to produce multiple beams of squeezed light. As in our previous talk, it has also been mentioned that people use many sets of OPOs to produce many beams of squeezed light. So if we can create many beams of squeezed light just in one vapor cell, that will be a very scalable method. And also you can use this for quantum imaging. You have an array of squeezed light that can help in the sensing. So then what do we choose to split? Do we choose to split a single photon state, or do we choose to split squeezed state? So in principle, you can do both, but experimentally, it's very, very challenging to deal with single photon state in vapor cells because of all the technical problems. However, 2 years ago, collaborating with Xinwang Du's group in Hong Kong, we managed to produce very nice photon pairs in vapor cells. But still, we are going to use squeezed light because that's simpler in the experiment. So first, how we produce squeezed light in vapor cell. The method is the so-called degenerate forward mixing, or people say that it's a polarization self-rotation scheme. So you just send in a linearly polarized beam, and then at the output, you will have a squeezed polarization state. Or in other words, if you send in X polarized light, then in Y polarized direction, you have a squeezed vacuum, which is the same process as mentioned in our previous talk. So this scheme has been demonstrated in the for the first time in Novatsky's group, and then immediately in Novikova and Mikhailov's group many years ago now. So then working together with Novikova and Mikhailov, in my group, we showed that if you use a coated vapor cell, the squeezed light can be cleaner, or it's much more unitary, meaning that the anti-squeezed part doesn't have that much noise. So how do we do squeezed light beam splitter? So we simply send in two spatially separated linearly polarized light into the vapor cell, and then you will have two squeezed beams. So let me show you how it works. So for example, in one optical channel, you have relatively small optical power so that it's below the threshold required by the squeezed light generation. And then we show that if you send in another laser beam at a distance from this weak laser beam, the squeezing, which was absent before just by this weak channel itself, now appears. And the strong channel will have its own squeezing. So it behaves as if the squeezing from the strong optical channel has been transferred or has been split into the weak channel. So experimentally, you see that without the strong beam on, there's no squeezing because it's above the standard, the short noise limit. But with the other beam on, you have some squeezing. So, so we can generalize this to a 2x2 array. So we send in 4 beams instead of 2 beams into the vapor cell. And we show that if we send in this little power in each channel, and if there's only one channel present, there's no squeezing, no light squeezing. But if you have if you turn on one more beam, your noise gets lower, and turn on another beam, noise gets lower, and turn on more beams, the noise gets even lower. So, so we also checked that any of the 4 beams have light squeezing, even though the individual laser power in each channel is below the threshold. So next, we are going to improve the squeezing. As you see, the squeezing is not that high yet, and we want to generalize it to a very large array, which is completely possible in principle. And then we are going to look into entanglement. So in the next 5 minutes, I'm going to tell you how you can use quantum control at a distance to realize non-emission Hamiltonian for light. So in the beam splitter experiment, I have shown you that the 2 channels kind of share the same spin wave, same coherence. But what if the coherence in different channels have different frequency? Then you can imagine that the flying atoms are still going to couple the beams, and it's going to mix the property of the light. So drawing here is to illustrate that if you send in 2 different kernels into the vapor cell, and then at the output, the kernel of the 2 beams might be the same because of the atoms mediating the coupling between them. So this work has been published here. So again, I'm going to skip all the motivation for why people are interested in non-emission Hamiltonian. And people have used optical systems to mimic this Hamiltonian because people found that using Hamiltonians that has certain parity time symmetry can give you very nice properties. But previously, most demonstrations has been in solid state systems, for example, in coupled waveguides or in coupled micro-resonators. So our motivation to do this kind of non-emission optics in atoms is to realize that we can have much stronger atom-light interaction, and the parameters are very easy to tune, and you don't have to do all this fabrication in the clean room. You simply create optical potential by light. And most importantly, we want to use some unique features in PT symmetry systems and combine them with optics and precision measurements. For example, you can use the exceptional point to enhance precision measurement and so on. So this is our experimental configuration. And again, we send in 2 different beams, but in each beam you have a pump and probe to form EIT. But the difference between the 2 beams is that the probe beam in one channel is red detuned. the probe beam in the other channel is blue detuned, so that the spin wave written down by the two optical channels have different frequency. So you can write down all the master equations to describe the system, and you can extract the effective optical Hamiltonian, or the Hamiltonian that governs the coupling between the ground state coherence, and you find that the Hamiltonian has a very nice symmetric form, and by looking for the eigenmode spin wave frequency, you can see that you should expect some kind of exceptional point behavior. So when, for example, when the frequency difference between the two spin waves is below the coupling rate between the two channels, you expect to have different EIT line widths between the two EIT eigenmodes, and above that the line width is the same, and the EIT separation should be 0, meaning the two EIT should be pulled together, even though initially the center of the two EIT are offset from each other. But by coupling with the atoms, the two EIT can be pulled together. This is in contrast to the energy expression in coherent coupling systems. Here we have deceptive coupling between the two modes. So interestingly, you can see that there is very interesting interference effect for two optical beams at a distance. These two, usually in an interference experiment, you have to overlap the two beams together at some point, for example, at the output, so that you can see interference pattern. But here, the two beams are never overlapped, but still you can see the interference. For example, if we let the spin wave phase difference of the two channels to be 0, in both channels you have nice EIT. But if you make the phase difference between the two spin waves to be pi, then EIT in both channels disappear because of the destructive interference. And when the phase is in the middle, you see a kind of dispersive EIT line shapes. So in summary, I have talked about precision measurement and spin squeezing schemes and quantum control at a distance. So here is my favorite slide. I want to thank all my hardworking students and all my wonderful collaborators. Heng Shen from Oxford University, Liang Jiang from Yale University, and Irina Eugenie from College of William and Mary. And Eugenie is also part of LIGO, so he taught me how to do a squeeze light in vapor cells. And Vladan Vulitic, he gave me a lot of help on spin squeezing experiments. And Jianmin Wen on weak measurement, Xinwang Du on single photon production. And I thank funding from NSF from China and Ministry of Science and Technology from China. Thank you.